issue of 7 and -1 versus 1 and -7. That hopefully this will be appearing very soon. That was resolved this morning on the chalkboard in the visitor's office, which is always exciting. So what I want to tell you about is, of course, the standard model effective field theory, as I asserted. It's worth just reviewing for a moment effective field theory generally, which is this tool set that we use sort of every way that we can come up with. Its job is to take a theory that we think we understand somewhere and tell us either where that theory is going to break down and stop working, or where that theory can be best understood as some other theory, because all of the contributions I care about are, say, super low energy compared to the dynamics of some sector of the standard model, so I can integrate out the WZ boson. And what it does, if you have a theory where you aren't asserting that you know everything up to arbitrarily high energies, which is, I think, a reasonable way of thinking about the state of our field, is it allows you to parameterize your ignorance about new effects and then constrain what those new effects are allowed to be without referring back to a specific model. So the general approach that underlies this is to identify the dynamical particles that matter to this calculation, and identify their symmetries, and then consider absolutely everything that's allowed by those symmetries, specifically including operators that are not renormalizable in UV, which parameterize this ignorance about what's going on at higher energies when I'm not probing. This really does need a really robust way of saying, I'm going to constrain things at this order, and knowing what that means, and being concrete about it and consistent with it in order to land on something that's meaningful at the end of the day. So the most standard example, of course, is Fermi's weak decay theory, where what we now understand to be a pair of quarks and leptons interacting with a W boson used to be just, well, here's an incoming neutron and 3 outgoing particles. This is a real legitimate limit of the standard model. It's calculable to arbitrarily high order in, say, 1/mw squared. We still use this today whenever we go about setting the parameters of the standard model by considering muon decays, which is one of the very standard input parameters to determine what the standard model parameters are. This is built to capture the physics in a particular energy regime. It does an expansion in powers of the energy of the process divided by MW. And you are able to systematically improve your theory prediction in this limit by considering higher powers in 1/mw and higher powers in electromagnetic couplings. And this ability to continue this series forward is the key virtue of effective field theories. You can identify more small parameters and expand in them. And as long as you're doing that consistently, it's very useful. So, a short slide for the people who think, but I already know which model I like. This is, by now, a completely ancient scare slide, but it's already scary enough, coming from Atlas for all of the things that are not supersymmetry, which is classified as exotics. And the fact that you can't read it is the point. They have searched for so many different things, and they have put bounds on all of the different things. And those bounds are now pretty strong. And those bounds are now comparable to the discovery reach for the long-term future of the LHC for those things they've already searched for. So it's now not so exciting to search for my favorite model as it is to say, well, what can I learn from the sum totality of this data? The SMEFT is taking this and applying this specifically to the standard model itself and saying maybe there's some new high energy physics somewhere else. Hopefully there is, because we have all these puzzles we want solved. The big open question in the standard model is the nature of this Higgs-like boson that we discovered forever ago now, 6.5 years ago. It feels like it hasn't been anywhere near that long, but it has. If we don't know anything about the properties of this scalar, then we can do an expansion in powers of this scalar over the electroweak vev or something, and new interactions, parameterized here by a covariant derivative, but generically insertions of fields other than that scalar. And this gives us what's called the Higgs effective field theory approach. But if, as we look at this Higgs-like scalar more and more closely, it continues to look more and more Higgs-like, which is what's been happening so far, it's entirely reasonable to insist that that scalar at 125 GeV really is embedded in an electroweak doublet that's involved in the breaking of electroweak symmetry. And if you do that, then you no longer are allowed to expand separately in this neutral scalar divided by the vev. Any interactions of the full doublet looks like new physics to start with. You end up with only one series in dimension over a high cutoff scale. In this Heft approach, it's necessary to resum all of these H over V's and treat those like form factors on every interaction that you study. So the leading order thing that you do is you actually insert form factors in front of, say, the electromagnetic coupling and whatever you like. All the dimension 4 things we understand. And you have to constrain those form factors before you can even start about the new high scale new physics. But because things seem to be pretty well behaved, I'm going to take this approach here and say all of my new physics ought to be heavy. There's not a big effect due to, for instance, mixing of the Higgs with another scalar that matters at this 125 GeV particle. So, in order to do something meaningful with such a theory, you need to actually know what all of the degrees of freedom are in the theory. Not the propagating degrees of freedom of the particles, but instead the couplings that exist in the theory. And this actually was searched for a very long time, and ultimately was found only in 2010 by people whose names are sufficiently difficult to pronounce that this gets called the Warsaw basis. And then the next thing that you would want is the behavior of this thing under the renormalization group. And this is actually the final paper that plugged in the last pieces of the renormalization of this thing at dimension 6. There were previous efforts that had done subsets of the interactions before. So this Warsaw basis is now our new best friend if we want to do model-independent physics at high energies, correcting the standard model. And this is approximately half of it. So you see, you get a whole mess of new couplings. You get field strengths cubed, higher powers of Higgs bosons, new corrections to Higgs kinetic terms, current-current interactions of Higgses and fermions, dipoles, corrections to what look like the coupling strengths of our theory, and also corrections to, say, the theta parameter, corrections to Yukawas. And you also get all of these for fermion operators. And if you don't want to say, well, I know this here about my UV physics, it should talk mostly to the Higgs, which is a reasonable guess you could make, then you need to treat each of these things on equal footing for both slides and say there's no reason that only one of these should be turned on or only one class of these should be turned on. So the first thing I want to tell you about is a calculation of loop effects on Z decays in this theory. So this is a place where the need for loops is completely manifest. This is our standard model experimental and predictions slide. And each of these predictions on the right-hand side is an incredibly painful 2-loop calculation with some leading 3-loop contributions that had to be done in order for that to make any sense. In fact, if you look through these values, these are matching very accurately, and if you compared them at tree level, you would have said, oh, the standard model is 100% wrong. So these loop corrections were central to really understanding what LEP has told us. And so if I'm going to plug in a correction to this, I'd better at least understand how big the error on that correction is. So the theory error size for one of these things is, well, a loop correction gives me about a 1%. A correction from higher dimensional effects from either a dimension 8 operator or from considering dimension 6 operators squared would give me an additional electroweak vev over lambda squared, which if I throw in for lambda sort of an optimistic, I'd love to solve the hierarchy problem with my new physics somehow, number gives me a 1% thing as well. The numerical coefficients leading these things, we don't know until we go and calculate them. So since the renormalization is known, you could do running of all of these couplings down to the Z mass from wherever you think it's matched at the high scale. That will capture the logs, the log divergences of your calculation. But for LHC scale physics, even for the Z mass versus say 2 TeV, those logs are not that big. So they don't desperately need resumming. You can do it. We have the technology to do it, so we do that. But it's not that big of a deal, and the pure finite effects that this RG knows nothing about can be of comparable size, because the logs just aren't huge. And in fact, there are known examples where things are corrected in a pure finite way. You never would have guessed that that operator mattered for this observable until you actually did the loop calculation, because the running doesn't predict that it will. So this calculation is performed in the limit of large Tafukawa, which is obvious, and Higgs self-coupling lambda, dropping all of the gauge couplings. That's mainly because the gauge couplings, it turns out, are hard by comparison. And this will give us a flavor of what these loop corrections are going to do to us. Only the QCD coupling could really keep up with these things. And that's going to give us all sorts of nasty effects that we didn't want to have to mess with. It turns out the gauge fixing is actually non-trivial in these theories at dimension 6. So if you're doing an honest one loop calculation that's a correction above a tree level contribution that includes gauge effects, then you're probably in for a relatively bad time. You need to worry about things like a non-trivial metric in field space, correcting what goes with which gauge boson, and all sorts of fun things like this. And actually, at the time that we did this calculation, even that level of structure was not fully understood. Our gauge independence is also trivial in this case because we don't have any gauge couplings in our loop calculations. We only have the tree level gauge coupling. And this is, in any case, a good first step toward the full MLO treatment of this problem. So you get a whole space of operators that like to contribute to Z decays, which are the things that we measured so accurately at lab. You get 4 fermion operators where you insist that this side is a top, because this is going to end up giving you something that's proportional to that fermion mass. The top mass is the only one that we haven't set to 0. And they can give you access to literally anything else in a final state. You also get scalar fermionic current operators, those Higgs, dmu, Higgs, psi bar gamma mu psi operators that we saw. Those correct the Z coupling explicitly when you put in Higgs BEVs. They also give you new structures that lead to these loops that don't occur in the standard model. But you need to torture yourself a little bit to make sure that they make sense. Gauge Higgs types operators, the sort that were, for instance, correcting the coupling strengths, or for that matter, the theta angles, would enter in this form. This operator here in particular is actually the one that we usually associate with the S parameter, which we like to think is super tightly constrained by left data, but it turns out that's only true if you only turn on S and T. If you turn on other operators, then they can cancel the effects of S and T, and S and T become almost completely unconstrained. And dipole operators will also give me an effect here, again, proportional to the top mass. Any loop calculation like this needs me to also calculate my input parameters at the same order, so that I actually understand what my Lagrangian parameters are in order to say something meaningful. So the canonical set which we chose for this calculation chooses alpha electromagnetic at the Z pole, G Fermi at Z, and the top and Higgs masses as these input parameters. The EFT actually corrects each of these things at tree level and again at loop level. We also think of the Wilson coefficients in MS bar as sort of EFT input parameters that we don't have a good way to have measured yet. Our goal is to measure some of them here. these final two here, M top and M Higgs, it turns out you can get away with only calculating at tree level, and that's because they don't contribute to the tree level decays in any way. So in order for these to show up at matter, you have to already be doing a one loop calculation. And as a result, the one loop correction to that would be a two loop effect and can be neglected. So you get a nice collection of exciting expressions when you go and do these calculations. Remember, this is only the top Yukawa and the Higgs self-coupling correction. You get things that, for instance, tell you the change in the coupling of a Z to a left-handed down type quark. This looks really extra super nasty, but it turns out a huge fraction of these effects come with this delta VR in front of them, which is sort of everything but that first line and the first and last pieces of the second line. All those other pieces only affect bottom quark behavior, and that's because the top mass is big and it couples mostly to the bottom quark. And that's actually kind of interesting in the context of LEP1 data, because there remain these sort of 2.7, 2.9-ish sigma deviations in the behavior of beat quarks in LEP data, notably the forward-backward asymmetry and the ratio to the hadronic cross-section, that it might be nice to understand better. Of course, it's also possible that every once in a while you get a 2-point-something sigma deviation from statistics. And combining together couplings of this form, you get things that look like sort of, you can get the hadronic width. And that just looks like the loop correction to couplings multiplied by the tree level coupling. So this is the tree level standard model coupling, the tree level standard model EFT correction to the coupling. So that's an order 1 over lambda squared object. And this, at loop order, is actually a mixed object. We've written that down as the standard model loops plus the standard model EFT loops. But the series is taken consistently, and we truncate our prediction here at order 1 over lambda squared.
So would there be something where there is no tree level, some loop would be generated by some theories where there is no tree level? So
absolutely, there can be. So there's a canonical example would be flavor physics, which I'll come to in a bit. But a similar thing, actually, previous to our calculation, this had been done in Higgs to gamma gamma, where that's also true. The standard model process is already a one-loop process. So in those cases, you can sort of cheat and get away with using only tree-level input parameter shifts universally, because all of your parameters only appear at one-loop order anyway. So if you take those expressions and you take these series and plug in actual numerical values, you end up with things that look like this. This is the tree-level correction to R sub B, which is one of the things that's a little bit discrepant, which is why I chose it. Then there are two loop-level corrections. One of them is the finite pieces, which is here. The other is log-enhanced pieces, down here. These you might have picked up the majority of by running, but notice there's two different logs. So if you define your couplings at the scale lambda equals m top, you still actually have non-zero effects from the differences in these masses. If you included gauge interactions, you would also get Z boson masses, W boson masses in these logs. These are comparable to these, and all of these things work out to be, you'll notice this is normalized to 1 on 10 to the minus 3 compared to 1 on 10 to the minus 2, and the coefficients are broadly comparable. So this is sort of a 10% correction to the leading order standard model EFT effect. So where I had asserted initially it should be 1%, it turns out the profligacy of diagrams gives you more like a 10% effect. So in order to learn something phenomenologically about this, you need to be able to count, and that's about it. The NLO corrections have introduced dependence on all of these different operators in this space. And at this level of precision, we really only have 5 z-pole observables. At one loop order, I don't like to talk about forward and backward until I include the box diagrams, which are not here, because they're gauge interactions. So clearly, I cannot constrain all of these Wilson coefficients based on 5 observables. It just doesn't work. And in fact, at tree level, there were already flat directions in the z-pole observables alone. And those directions are lifted by triple gauge coupling measurements, which are pretty weak by comparison. So they're very weakly lifted as flat directions in my parameter space. With all of these relevant parameters, it's clear that all of the electroweak precision data is not going to be enough to close a curve and say all of these things must be within some amount. So these loop corrections cannot be constrained by electroweak precision data alone. And that means that your tree level electroweak precision bounds can never really be meaningfully more precise than this 10% factor. That 10% factor is multiplying a different Wilson coefficient. So when you constrain a Wilson coefficient to be order 10%, you can't get much better than that with electroweak precision data. And these constraints sort of naively give you constraints that are at the 1% level, at tree level. So the moral of the story is that if you're believing those tree level constraints, you're missing something important.
So also, all those effects are coming not only to the left-handed fermion interactions, but they can, or left-handed parts of any interaction, but they can also come in some right-handed.
Absolutely they can. So these operators that have D's and U's, for instance, are talking about right-handed fermions. And this already at tree level, you see the effects on right-handed fermions coming
So
from this.
what's the difference between this small d and capital D?
This is a derivative.
Oh, this is the derivative.
Yeah.
Ah, I see. I see.
Yeah, unfortunately, I don't have a second projector to just leave the basis up the whole time. That would clarify a lot of these issues. So then the question becomes, if all of our electroweak precision bounds can't get better than these 10% numbers, which is a bit depressing given how precise the data is, where can we get other bounds that can fix that problem for us? Where else can we look? So there's a big, huge pile of data that isn't just LEP, and we want to use it. It turns out these electroweak precision measurements have already included things like Tristan and other low energy measurements. But we now have the LHC, and we already had the Tevatron. So it'd be awfully nice to plug those things in as well. So the canonical way of doing this is you say, okay, very good. I have a Monte Carlo program. I'm going to feed it an EFT type interaction, and I'm going to believe what comes out of it explicitly, and then I'm going to constrain that. The big challenge with that is concern about the consistency of your EFT, because you're now looking at things at higher energies. Your expansion parameter, E over lambda, has gotten less small than it was. So this is going to break down when the new particles are accessible, for sure, and your confidence in how good your prediction should be getting weaker and weaker long before you reach those new particles explicitly. Ensuring EFT internal consistency is really the best way of getting something model independent. And internal consistency, I mean, treat the EFT like a theory. It has a new coupling, expand in it properly.
And it's a, so far it's a flavor space wise, it's universal.
That's right. So the ideal EFT search would do something like this at the LHC. It would treat the theory errors coming from higher orders in the expansion as some sort of measurable nuisance parameter. We wouldn't know how to predict how big the effect should be there, but if we could isolate it and remove it, life would be great. This is often possible for, say, systematics. The experiments go and measure their own uncertainties on their B-tagging efficiencies, for instance. It's occasionally used for, say, normalization of electroweak corrections. But since we aren't calculating this here, we would have to rely on the EFT structure to do it explicitly. And the only really robust prediction of EFT is that we should get a power series in the inverse cutoff scale. So maybe, just maybe, I could be able to write down my prediction this way. And look at dijet mass, for instance, for dijet production, integrate it over the angles to remove any angular differences at higher orders, and then I could get a cross-section, which is the standard model cross-section times 1 plus some series. Because I know that if my expansion is supposed to go like the energy of the event divided by lambda to an appropriate power. The signal, the thing that I can actually calculate, would be the linear term, the first term here, C1. And everything else would be noise. that I don't understand, but I maybe don't need to. And the theory error would hopefully be probed by the sensitivity to the trunk of this series, wherever you stopped. Sadly enough, that is not the shape of this cross-section, because we can get part of the next order in this series by squaring the dimension 6 operator without needing to write down a new basis and do a whole bunch more work. And it already doesn't follow this behavior, and that's because you have access to different PDF distributions at different orders in this expansion. And those grow at different rates. Grow or shrink with x at different rates. So that means that my errors really can't be fit away cleanly for unknown higher order effects. Not a terribly big surprise. We can't fit away, say, alpha strong cubed effects on something that we calculated at alpha strong squared. So a combination of signal shape fitting with a meaningful error estimate, we can estimate the effects of an alpha strong cubed calculation that it would have on a calculation we've done at second order in alpha strong. That's the best we're going to be able to do. So my signal distributions in dijets look vaguely like this. Chi is this angular variable, it's an exponential of the delta y. I get two distributions, one that's centrally peaked and another that's pretty flat. That kind of looks more like a T-channel exchange in its behavior. And these are both occurring at linear order at 1 over lambda squared. You can actually calculate for a fixed center of mass energy what this linear combination looks like. As you change center of mass energy, these coefficients change a bit, again because of changing PDF numbers, but they don't change much. And this angular difference remains robust at all energies. So this is two linear combinations that you might hope to be able to constrain. So what you do is you go and look at the last time people tried to do this, wrote down these operators, and say something. Back then they were searching for quark compositeness, which is a search proposed slightly before I was born. This is not really an EFT treatment. It's meant to be a specific UV model, and as such they don't truncate in their couplings properly. To do the EFT expansion, you need to consider explicitly the errors arising from the unknown dimension 8 operators or other neglected operators that you've turned off, which also happens in this analysis. And you need to investigate the effects of all the operators at that power counting order, not turn off things at dimension 6 that could matter.
So this dijet EFT, so this is the effective dijet. So what does this mean? Because the jets also can come from ISR and those ways. So, but this is what? This is just the dijet EFT.
So this is the EFT contribution to the dijets. These C's here are Wilson coefficients.
Okay,
they should be thought of as including a 1 over lambda squared. And this is the leading order contribution from
Just
effective
to
operators to dijets.
This,
so the standard model still exists and makes tons of dijets. But these would be our signal functions on top of the standard model in some arbitrary units. So the search signal that had been used in these compositeness searches, both at Tevatron and at the LHC, has kept all of the terms naively predicted by the dimension 6 operator, including the squared term. The squared term is very strongly centrally peaked. And so the natural thing to do, given that assumption,
centrally peaked. What does it mean? Squared term is centrally peaked?
Centrally peaked, meaning at low rapidity. Low absolute value of rapidity. It contributes most to central interactions, which is what you expect for a heavy new particle generally, right? So a search in angular variables was a natural technique there, and what they did is they actually searched, they normalized out the cross sections and searched in the angular distribution of the jets alone. The consistent EFT treatment is to expand the observable that you're measuring in the power series, not the amplitude, but the cross section. And that gives you a different answer. You have to include all of the contributing operators at dimension 6. We really only have those two distributions that I showed you earlier, so that's not too bad. There are small differences coming from PDF evolutions. Since we have the full dimension 6 contribution, really everything else needs to be discarded And the dimension 6 squared piece, which will go like 1 over lambda to the 4th, is a reasonable guess for how things that go like 1 over lambda to the 4th should go. So we use that as a proxy for the size of the unknown total dimension 8 contribution. Of course, the additional operators don't have to follow the same angular distribution, but this will give us an idea of the size in a given bin of that error. So if you take out this normalization, if you keep the normalization, you learn nothing. If you've normalized out the fact that you're producing more or less digets, then your errors become way too large to be useful. If you take the normalization off of the analysis, then there can be bigger systematic differences between the signal and background. So this is what you get for 2.6 inverse femtobarn, which was an early study number. These things are bounded by the EFT error. At low statistics here, this is statistics plus error, plus theory error. You notice the theory error at this end doesn't matter much. These are already bounded by the theory error, the most central ones. That's because our 1 over lambda to the 4th distribution was centrally peaked. But the errors out here are shrinking fast. And that's just because we get a better measure of the background. You actually end up with multiple bins 1 sigma away, and you can learn something from this. This is for 50 inverse femtobarn at the LHC. It's interesting to note that the EFT signal size is only sensitive to this linear combination. That's always been true, and in fact, it's pretty common for people to normalize the lambda into this coupling. This is broken weakly by RG effects again. It leaves you with 2 meaningful ways to interpret the bounds coming from any search for an EFT. You could say, okay, well, I'll fix where I think the new physics lives and put bounds on the couplings, or I'll fix the couplings and get an idea of how high the new physics lives. So if I fix the couplings, my reach in cutoff scales looks something like this. If I have turned on only the flat distribution, my reach is pretty bad. And this is, the 2 colors are if I think there's 1 operator at dimension 8 that gives me error versus 10. And if I think there's 10 operators at dimension 8 which contribute, which there probably are, then even at the high Lumi LHC, for these fixed couplings, I won't see anything. I won't be able to learn anything. If I turn on the centrally peaked operator, or I turn on both in a way that positively interferes rather than canceling each other's effects to some extent, then I can really end up with bounds that are pretty robust in this space. And this is for couplings of order 1. If you have couplings of order 2 pi, then your bounds get notably stronger, which was the canonical guess for composite behavior, just because we wanted things to give us 4 pi-ish things for strong coupling. If you fix the new physics scale instead, and see what bounds you get on the Wilson coefficients, this is for fixed luminosities now. This is 100 inverse femtobarn, which we now have. We should now have bounds in some region of parameter space for lambdas of 10 TeV. And with 3 inverse atabarns, we'll get more robust bounds. The most interesting point on this plot is a point close to 0, 0. So I've zoomed it in here. You can see we are making meaningful gains in these coupling strengths. Notice the differences in normalizations of the x and y axis here, though. That centrally peaked one, we're pretty good at bounding. The flat one is much more difficult. It just contributes less to our total cross-section, and it contributes in a way that's less different from the standard one. So this is the first example of bounds coming from LHC analysis that actually included an error assumption in this new series in 1 over lambda squared. The next thing we went on to do is to study dileptons in the same sort of way. There's a set of 7 dimension 6 operators that contribute to dilepton production at high energies with a growing relative to the standard model behavior. There's another set of operators that contribute proportional to the standard model, not growing. But if you look out in the tails, this is what you expect to be able to see most of. The 4 fermion operators here are the ones that give us those, and we have 2 distributions once again. That's why I have 2 separate tables here. One of them, unlike in the Decays case, both of these give you comparable behavior in mod eta. But one of them prefers to make the lepton forward, and the other prefers to make the positron forward. So you need a slightly different distribution to see how they're behaving. You need to have negative etas in addition to positive etas available to you. And what you get at the LHC as a result, because the LHC doesn't have a well-defined forward for any given proton-proton collision, is your forward is defined by the direction the quark comes from, and the quark tends to be harder because there are valence quarks in a proton. So forward, this is the distribution for the electron. The forward operators tend to give you electrons that are at higher mod eta, and positrons that are at lower mod eta, and vice versa for the backward type operators. These distributions, again, have some small PDF dependence associated with their coefficients, but there's meaningfully 2 linear combinations that we can hope to bound. And if you go through the same exercise that we did in the Decays case, but look at the leptons instead, you end up with bounds that look like this. Now this is for different sets of couplings, and we've set N8 to 20 to be conservative, because N8 didn't matter very much, so we wanted to throw in a number that felt like it was reasonably safe. And this is actually based on a current LHC curve here. This curve, there was a deviation from the background expectation there, so this thing is not mirrored on the other side, it's all the way back there. It's sort of preferred a central value like this. We should not be surprised then when the curve moved back to these more centered around 0 things in the future, unless if we're really seeing new physics in this distribution already. We also did the same search at the tevatron, and here you can see the difference between 1 and 20 in N8, and it's not huge. To see what bounds existed already at lower energies, and extracted these from current tevatron data on dilepton production. So yeah. If you compare these 2 things to each other in a more natural space, you end up with this beautiful looking plot where the Atlas data is really nice for constraining high energy new physics, but because a lot of its data is at high energies itself, the errors get big. And down here, the tevatron actually takes over and gives you the best bounds. So despite what I said earlier about C over lambda squared being the natural thing to bound, if C and lambda squared had that natural behavior, and you really thought, okay, I've bounded the combination C over lambda squared, then this curve here would be the bound that you would write down for yourself from the tevatron. And this curve here is what you would be expecting from the 300 inverse femtobarn search in Atlas. But you notice that we're losing sensitivity earlier than that because we actually have these errors that do separate the Wilson coefficient and lambda. Because there's unknown Wilson coefficients at dimension 8 that still talk about the same lambda, it's the same scale where the new physics takes over, but you have some unknown Wilson coefficient that you have to keep from getting below, say, 1, to not be saying, ah, well, because at dimension 6 this thing is tiny, it must also be tiny at dimension 8, which is a thing that does not follow. Okay, so the LHC is a reasonable place to look. I've shown you a couple of the simplest observables available to do that. But there's other places to look too. Huge piles of lower energy data as well in the context of flavor physics. So EFT treatments down here below the WMAS are completely standard. That's the example I showed you earlier. Relating flavor data to at least some of the standard model EFT has been a long-running enterprise. It turns out if you include flavor non-universal effects, the full parameter space of this thing is just short of 2500 dimensional, which is big, far too big. in order to land on something that makes sense to think about seriously, you need some kind of organizing principle, I would argue. And the fact that flavor constraints are already very severe on new physics tells me that exploring the standard model flavor structure feels like a natural thing to do, to reduce this number to a handy number that I can sort of conceive of doing a calculation using. So if you apply minimal flavor violation to this, you end up with that's of course the insistence that all of your flavor violation is coming entirely from Yukawa couplings, standard model Yukawa couplings. If you turn on arbitrarily high powers of the Yukawa matrices, you actually get back to a full flavor violation basis. But if you say, well, the top coupling is big, the bottom coupling is kind of big, the others are small enough that I'm going to neglect them, you end up with this approximate U2 squared flavor symmetry between, say, downstrange and up charm, and top and bottom can go and do their own thing completely. If you instead say, I'm going to constrain myself to a finite number of Yukawa insertions, and then you make that finite number 0, and you also insist on CP symmetry, which is, if anything, better constrained than flavor symmetry violating effects, you end up with 16 plus 20 parameters. 20 is the 4 fermion operators here. Linear flavor violation, allowing yourself exactly one Yukawa matrix, turns on another 11, and these are almost all dipoles. You have dipoles and Yukawa coupling corrections that get turned on by allowing one insertion of a Yukawa matrix. The standard model loops still generate completely obligatory flavor violation. You have a W boson, it breaks flavor symmetry, so you're going to get the new physics interactions multiplied by standard model flavor breaking effects. And that will give you a minimal possible new physics contribution to flavor in this minimally flavor violating theory. So given the generically loop origin of flavor violation in this ansatz, we choose to focus on things that are loop generated in the standard model already, so we have a chance to see them. That would be down-type FCNCs. It gives you access to the top Yukawa, which is huge, and it gives you something relatively small to interfere with. The weak effective theory operators that are of interest here are dipoles and 4 Fermi interactions. Dipoles with QCD and QED, and 4 Fermi interactions, the most interesting of which are the ones between BS and L plus L minus, just because those are cleaner to measure. So those are these operators 7 through 10 in the standard basis. In trying to do this matching, you end up with a whole bunch of contributions. You get a whole passel of 4 Fermi operators that are going to contribute. These are 4 Fermi operators that couple up-type quarks to leptons on this slide. And so you get tops internal to these loops, because the top mass is huge. And you get flavor violation from this whole set of different things. This one's particularly entertaining because that's actually a charged current 4 Fermi operator, which you then get a sort of T-channel looking W boson. Most of the 4 Fermi operators that are contributing have this form. And the charge current loops give you the flavor changing effects, charge either current or charge scalar, as the case may be. All of the pieces that are top mass independent end up canceling by gem mechanism calculations, as we've all seen before in other contexts. There are, it turns out, 2 operators that actually do give you tree level flavor violation even in the 0 Yukawa matrices allowed space. And these are the operators that couple 4 quark doublets together, because there are 2 different flavor contractions available here. I can contract my anti-doublet in one of the currents either to the doublet in the same current or to the doublet in the far current. And that allows me to actually get something like a BS transition with some arbitrary uptype quarks down here with appropriate CKM matrices. In the end, your CKM matrix becomes part of your definition of the doublet, so this isn't terribly surprising. these will run into the observable operators, the ones having to do with either BS gamma or BSLL at one loop order, or even in the weak effective theory, that running has been calculated. We can do a calculation of this form. In fact, this is exactly the calculation you have to do in the weak effective theory, or in the standard model EFT. It looks the same. And you get a contribution from the tops here that don't exist in the weak effective theory directly to the Wilson coefficients of the dipole and of the 4 Fermi interaction of leptons. Higgs leptonic currents contribute also in interesting ways. One of the things that these do is if you throw in 2 Higgs VEVs, you end up with a correction of the Z coupling to 2 leptons. And that's actually one of the most strongly constrained things in our naive tree-level electroweak precision searches, because that was how we made the Z. But you also get new graphs of these forms, with these weird 4-point interactions that are manifestly higher dimensional. And if you forget about these, then the answer that you calculate ends up being gauge parameter dependent. So it warns you pretty loudly that you've done something deeply wrong. The Higgs leptonic triplet operator also gives me corrections of the W and Z coupling to leptons. The W is an interesting feature that wasn't true in the singlet operator. And these again also generate new diagrams that are going to be important for gauge invariance. They also give me these box interactions. The Higgs quark current operator does the same thing about shifting the Z coupling that I had mentioned previously. It does it to the quarks instead of the leptons. So you get these sort of naive standard model looking graphs, and you also get graphs that include a charged Higgs coupling here and back out to the B quark. With again explicitly higher dimensional operators inserted. And the theory once again shows up and warns you when you've done it wrong and forgotten a graph. It's very timed that way. And just like in the previous one loop calculation, there's also input parameter effects to be calculated here. Now, because these beta S transitions are all loop order, in the standard model, I can get away with using my tree level input parameter shifts here. But it turns out that even the tree level input parameter shifts had never been considered in a flavor analysis of this type previously. So the matching calculation has been done in the past, but it was done assuming that the Lagrangian parameters had numerical values, which is something we've gotten used to thinking about in the standard model because we defined them forever ago in terms of very precise measurements. But it turns out that the EFT operators contribute to those very precise measurements and shift around what you think, for instance, G Fermi actually is. If you have a 4-lepton contact interaction in the standard model EFT, that's contributing to muon decay, and it's changing how much of the muon decay is actually due to the W boson. So when you go to try to extract the behavior of the W boson from G Fermi, you get a wrong answer if you forget about the fact that the EFT can contribute there. So this
EFT is based on the assumption that standard model gauge symmetry.
It's based on the assumption of what, sorry?
That standard model gauge symmetry is the only gauge symmetry.
No, it's based on the assumption that the standard model gauge symmetry is the only gauge symmetry that's dynamical at this energy scale.
Yes, so whatever.
So
I
any
can have
new
another
gauge
gauge
boson
symmetry.
must be heavy compared to the B meson.
Yeah, so standard model, like a W is heavy enough, so I can have another WR, for example.
You absolutely could, and if the WR was up there, it would not break this effective field theory in any way. It would just be able to integrate out into these operators, because it's too heavy to be dynamical.
I can have a different diagram. So here, for example, you have a BL, SL, and then Z. I can have a BR, SR, some Z prime, and then that can give you lepton, or whatever you want.
Yeah, so that looks like this.
Yeah, but don't you have?
I can integrate out your new boson that's coupling to my leptons.
Yeah, but if you have a particular, if you have W, then your chiral structure, operator structure has particular form. And if I have a W,
both of the structures exist here. So if you have a W prime, it actually looks like this one.
Like, yeah,
And both of the chiral structures exist in the standard model EFT to account for that. So if this thing is heavy compared to the Higgs VEV, then its contributions are explicitly included in this calculation.
so
They're
any,
included in the form of an effective operator at dimension 6 in the standard model EFT, but it's there.
so both for left, right.
That's right. Everything that is allowed by the standard model gauge symmetries that doesn't break a standard model charge at this 4 Fermi interaction is included in this calculation.
NS, massive.
The D is massive and S is massless in the numerical expansion we've chosen to do. Adding in the S mass would not be hard. It's just not numerically interesting. In fact, we are finishing up the calculation of kaon oscillations, which is as part of this process as well. And there we need to keep the charm mass. Turns out the S mass is not important to kaon oscillations, but the charm mass definitely is. So this is actually going to give us the leading order contribution of a flavor universal high energy theory. Any flavor universal high energy theory, contributing a leading order in it in 1 over its cutoff scale to the flavor observables in the down sector, which are the best measured ones. So what we've done in this paper is actually the matching. This is going to appear by next week, assuming something else doesn't show up and confuse us for another extended period of time. We have a follow-up in the works already, taking those, running them down to the B scale and to the K scale, and actually learning what linear combinations are constrained of these flavor symmetric operators based on that. Explicitly flavor asymmetric operators have been considered copiously in the literature, basically because that's very easy. It's all tree level. So that's already out there. We were able to compare some of our calculations to previous literature because people had talked about top-specific operators. So we can compare our mass-dependent pieces to their mass-dependent pieces and learn what's going on. But they have additional contributions in those theories coming from renormalization running that's not canceled by Jim. So I think this is going to be a pretty useful result in the end. It's going to give us a whole new spate of linear combinations that we can constrain. So in the dijets, you saw 2 linear combinations. In the dileptons, there were 2 more. In the precision electroweak, I mentioned there were 5 observables, which will bound 5 linear combinations of these operators. When you turn on strong enough flavor assumptions that you end up with something reasonable, so linear MFV, for instance, then you need, in the end, to find something on the order of 50 different constraints in order to close this curve. If all of those constraints come in linear order, doing the global fit is entirely an exercise in linear algebra, and therefore the computer will suffer, but I won't. So I think this is a promising direction of future research that's going to ultimately lead us to something that can say, whatever new model you come up with, whether it's a right-handed SU2 or something that no one has thought of yet, if it's heavy, you can map it into standard model EFT Wilson coefficients by integrating out the heavy new physics. Once you have done that, we will have constraints that you can trivially compare to your theory. In fact, it's worth noting that tools to do that matching at 1 loop order are, to do some of that matching at 1 loop order are done, and to do a full 1 loop matching are underway, and have been promised to come out in a year for 2 years now. So they're meant to be any moment now. And I actually keep bothering these people because I'd really like to see that. They say they're making progress. These NLO predictions are under-constrained by our highly precise data, and at the moment what that means to me is our left data in this context is kind of going to waste. So we need to find other constraints that are out there, even if they're relatively weak, that can constrain the things contributing at loop order, so that we can then actually use our left data to get stronger constraints than what we're seeing here, down to the level of 2 loop type effects at that really 1% number that we're able to get. But we have to do that in an intellectually honest way, acknowledging this new perturbation theory expansion has new errors associated with it. And in particular, not keeping the pieces that are part of the error in our signal just because they make our bounds look better. So there's a lot left to do in this direction, but I think it's an exciting exercise in trying to find a way to make the LHC and all of the previous data that we have in particle physics have utility for ages to come, for new models that get thought up, and to guide where we should be looking in our next experiment, should it ever get funded. Thanks very much. Thank you, Will. Are there any questions?
So I always have this struggle with EFT. So I see that you can constrain 5 dB, 6 dB, but with a direct production, like where LHC is sensitive to, at that time I don't see this constraint of any use. For example, suppose I have a given model and I have a resonance, I use the resonance search.
Yes.
And to constrain that. And there I don't see the EFT can be used.
So what the EFT can be used for is, imagine that we build the LHC upgrade and we're trying to tell the experimentalists what signals to target. The EFT may or may not have already told us that this theory at a scale of 8 TeV would have been seen in the tails of dilepton production, even though we wouldn't have seen the resonance effect. And then you could say, this is not a particularly promising target. You should invest your energies elsewhere. Actually, it's most useful as a guide to model building, because it provides these completely conservative bounds that tell you this model would have been seen. So you can learn something very effectively about, I'm going to write down this new theory. I get excited, I write something on the chalkboard. I plug in a trivial looking Lagrangian into one of these matching tools, and it runs that through the observable space, which is going to be fairly easy in the context of a program that's under development called Wilson, that runs things all the way down to flavor and all the way back up and everything else you could want in between. It gives you a likelihood for your model based on these conservative bounds. And it can tell you, this model is already rolled out, and these are the observables that did it. That would be super useful to know.
So let me give you a particular example. So now we all are kind of a little bit excited with this RK star, RK star. And there are many models which we are building and which are all surviving at the scale of between 1 to 2 T. LHC does not have any constraint, and we can bypass all other constraints.
So what that's telling you is
right,
that
how EFT is going to give us anything new for doing.
So if you look at the publications of Grelio and others, Adler Grelio, he has looked at the EFT effects for heavy new physics and said, in this case you can see something, in this case you cannot.
In fact, Grelio, I was in touch with Grelio. In fact, that paper I'm seriously having some trouble with, because based on what they claim, and then you used it to resonance search, you get a different parameter space.
So resonance search should generically give you a stronger constraint.
But they found that EFT is giving the stronger constraint. So I don't think that paper at the end was correct. But because they did something, some assumption somewhere. But
what this is telling you is that things that are here do not yet include these models. And I would argue very strongly that once the LHC says, I want to look for exactly this silly leptoquark doing this silly thing, that they will find it if it's there at 1 TeV. If it has a leptonic final state, you really can't avoid it.
Actually, then we should look at the model parameter space for many of these explanations. LHC does not have reach.
Because they have to be pair produced in that case.
Pair produced, or it doesn't matter. Like LHC does not have the reach, so it can be pair producing, reproduced. So there are different ways. And there is no EFT constraint that could be applied to those models.
I suspect that you could apply an EFT constraint if it were calculated properly. So what may well have happened in Abner's paper, which I didn't look into in much detail because he was looking at a flavor scenario that I didn't care about too much, is he may have played this game that I mentioned in the core compositeness case of keeping this squared term as signal instead of using it as a meaningful error estimate. Because this squared term, it turns out, is pretty big, especially if your scale is relatively low, it becomes huge.
Yeah, so because I can give you one example with a maybe detail later on, and then you can tell me like whether really EFT has any constraint. It doesn't have to be flavor, just even flavor symmetry.
Mm-hmm.
Not necessarily. I'm just citing this flavor because we have.
A search that's designed for high energy new physics is not going to be great at finding new physics at 800 GeV. It's the same story as one that's designed for finding new physics at 200 GeV. That Tevatron is not going to find 2 TeV new physics.
So, for example, then between 1 to 3 TeV, where LHC is not doing much, then and suppose if you want to build a collider there, then how EFT is going to guide us?
Well, you have to actually go back and look at the data that comes from the collider that's there.
But
And
as
you
I
can
said,
learn something about its bounds.
it's not bounded by, let's say, any of these analyses.
So the
Because-
Tevatron is bounding regions that the LHC isn't. So if you look back in further historical data, you can actually get EFT bounds on lower energies than the LHC is able to do. Because the errors are smaller, because I'm probing smaller energies.
Maybe
So this is an excellent example right here. It's sort of peak at 1 TeV in sensitivity to things that give you dileptons.
I think the best way one could answer these things, I can give you one model example and see whether you can find any constraint from Atlas, LHC or any. And then one would know that really whether we are getting a guidance. So that would be the best.
I suspect that what's happening is the operator that you're instituting is a dimension 8 operator. Because it involves 2 propagators of your leptophore.
No, it's not a leptophore model. It's a different model.
For a singly produced particle model, I think that that's going to live in this basis. And it is entirely possible to say I can bound that or I cannot. If you have to pair produce the particle, then you end up producing things at first order in the cutoff scale of 1 over the cutoff scale 4th. Because you get particle mass 4th in the denominator there. And if you don't get particle mass to the 4th there, then you have a resonance search, and you should do that because you will get guaranteed better bound.
No, actually that's the thing. Like if the way I see it, if the resonance search fails, because resonance searches also has this branching ratio and many things, and if they can fail, and there is no constraint from Tevatron for those bounds.
So they can fail because you're making jets, and jets are messy, and the standard model backing is huge. And if you're making jets mostly, then I'm going to have the same problem. My bounds on jet operators were very weak.
Yeah, so maybe the EFT is, that means at the end, for those kinds of models, EFT is not telling us anything new compared to the regular.
The EFT does not tell you anything new for models of 1 TeV new particles, because the LHC should have made them. So the LHC already told you all of the story you can get there. The interesting point is if you think you have physics that should still be solving the hierarchy problem, or something else that ought to have reasonable sized couplings to final states that are spectacular, then the EFT will tell you, well, maybe it's just a little too heavy, and here's what we know about all the things that are just a little too heavy.
So for example, if one gets another type of collider, instead of, since EFT or resonance search, they are not teaching us anything new there. And one can try to think about, suppose, a muon collider or a plus and minus collider, to look for new physics, since the EFT and resonance search has not.
EFT actually gets much cleaner bounds and is most naturally applied in an E plus E minus collider.
Yeah, so that means it's a, well, different
anytime you make a
than
precision
collider.
measurement, you get an EFT bound on something.
Yeah,
That is
so
how
that
this
means
works.
you need another collider to understand physics at that. Not necessarily LHC or EFT at the LHC is teaching you everything.
No, at the LHC alone, it's absolutely not, which is why, for instance, we're working on flavor physics and we're working on lead bounds at one loop. You want to include all of the data available. The LHC is actually a relatively unnatural place to try to apply EFT compared to these other things.
That's what the way I always
Yeah, absolutely.
understand that. It's very unnatural.
It's also the best place to get a bound on 4-quark contact operators, unfortunately, that will be screwing up your data, so you still need it. But that bound will be weak.
Any other questions?